General Plane Motion by Feriza S.S.W. In general planar motions, bodies are both rotating and translating at the same time. As a result, we will need to relate the forces to the acceleration of the center of mass of the body as well as relating the moments to the angular acceleration. As you can see in this picture, this star is being rolled along the ground is an example of general plane motion. The tire is both translating and rotating as it is pushed along. These are the formulas that we are going to use to analyze a body undergoing general planar motion. We will start by drawing a free body diagram of the body in motion. Be sure to identify the center of mass as well as identifying all known and unknown forces and known and unknown moments acting on the body. It is also sometimes helpful to label any key dimensions as well as using dashed lines to identify any known acceleration or angular accelerations. Next, we move on to identifying the equations of motions. At its core, this means going back to Newton's second law. Since this is a rigid body system, we include both the translation and rotational versions. We will break the force equations in two components, turning the one vector equation into two scalar equations. Additionally, it's important to always use the center of mass for the accelerations in our force equations and take the moments and moment of inertia about the center of mass for our moment equation. Taking the known forces, moments, and accelerations into the above equations, we can solve for up to 3 unknowns. If more than 3 unknowns exist in the equation, we will sometimes have to go back to kinematics to relate quantities such as acceleration and angular acceleration. You are designing a frisbee launcher to launch a 40 cm diameter 0.6 kg frisbee that can be molded as flat circular disc. If you want the frisbee to have a linear acceleration of 20 meters per second squared and an angular acceleration of 50 radians per second squared as shown to the right, what should force 1 and force 2 be? I have here the free body diagram, and in the right side is the mass acceleration diagram of the frisbee. This is force 1 and this is force 2. This is the center of the frisbee. Unbalanced forces cause acceleration, let's say in y direction, and they produce a rotational acceleration which causes vector I, alpha, in the direction shown. And let's choose this point and give it a name like point A. We have here a mass of 0.6 kg, a diameter of 40 cm, therefore the radius is 0.2 meters, and an angular acceleration alpha is 50 radians per second squared. And your acceleration in y is 20 meters per second squared. So observe that we are interested in F1 or force 1 and force 2. Clearly, one equation is net force in y direction is equals to MAY. Another equation is counterclockwise to be positive and moment in all vectors about any point such as A on free body diagram must be the same at the moment of all vectors about the same point as mass acceleration diagram. So, if we are looking for force 1 and force 2, so in mathematical point of view, we need 2 equations and 2 unknowns. So if we are going to choose the equation of moment in all vectors about any point such as A on free body diagram must be the same at moment of all vectors about the same point at mass acceleration diagram, we will notice that force 1 is eliminated from this equation. And if the only force that has moment about point A, therefore Using the moment equation, we have 2r times force 2 for the left side of the diagram equals to the moment of everything about the same point A, which is sum of alpha, which is already a rotational load, plus moment of MAY, and this distance is R times MAY, which this approach we have one unknown. So if we apply again the numerical values of 2 times R, or the diameter is 0.4 meters, times F2 or force 2 is equals to, I recall that I is 1/2 times 0.6, and the radius is 0.2 squared times alpha, which is given as 50 plus the radius of 0.2 and the mass is 0.6, and point A sub y is 20 meters per second squared. All values are numerically known except for force 2. So, solving for this equation for force 2, we have the value of 7.5 newtons. For force 1, we will use this equation, which give us force 1 plus force 2, which is 7.5 newtons, is equals to 0.6 times 20. So this gives us a value of 4.5 newtons.